All right, so today, welcome to our RC Circuits Play Posit. This is going to kind of prepare us for our lab tomorrow. So today we're going to be applying Ohm's law and some Kirchhoff's laws, as well as a little bit of differential equations to analyze the behavior of an RC circuit. And an RC circuit, as its name implies, has an R in it, a resistor, and a C in it, a capacitor. So we're going to start off with a little bit of loop law and some pertinent equations, talk about RC circuits, use some differential equations, examine these circuits as the capacitor is charging and as the capacitor is discharging, and then talk about what I'm going to call sometimes transient versus steady state, where transient kind of means time equals 0 just after we make a change, and steady state is like a long time after. All right, so what the heck is an RC circuit? Well, before we get there, let's just remind ourselves of our loop law. And remember, our loop law says that for any path we take around a circuit, our total voltage has to equal 0. Any voltage that gets introduced has to get used up. And I want to remind us, for a capacitor, that voltage is given to us as the charge on the capacitor over C, which is where C is its capacitance. And for a resistor, it's given this way as IR. The last thing we're going to need is to remind ourselves that current is related to the rate of change of charge. It's the rate of flow of charge. So I'm going to mess around with that a little bit in a minute. So those are the three things we need. All right, so here's an RC circuit. In this RC circuit, we're going to take a capacitor that's already fully charged. We'll talk about how that happens in a moment. But we take a capacitor that's fully charged. So it starts off with some charge Q0 on it. And we're about to connect it. We're about to close this switch in order to connect it to this resistor. Now, when we do close that, what's going to happen? Well, we've got a positive side and a negative side. So our capacitor is going to kind of release its energy. It's going to kind of act as a battery. And we're going to get some current that flows this way from the positive side to the negative side. But it's only going to flow for a little while until the charge on the capacitor equalizes, and then it's going to kind of peter out and stop. So once the capacitor is empty, it'll kind of go, it'll let out all of its charge, all of its current, and once the capacitor is empty, it'll stop. So let us kind of look at our loop law here. So we're going to take a little walk around our circuit in this direction. I'm just going to start here for kicks. So as we're going, we're going to cross our capacitor and remind ourselves that the voltage of that capacitor, okay, we're going from negative to positive, so it's going to increase. So we're going to end up with Q over C. So at any given moment, the amount of charge on the capacitor is going to be some function of time, right? The charge will diminish over time. So we'll write Q over C. And now as we go over our resistor, go across our resistor, which initially there's no current flowing, but once we close the circuit, there will be some. Once we close that, we'll end up with minus, because it's going to be a voltage drop, I times R. And we want that to be equal to 0. Okay. So I'm going to mess around with this a little bit, and I'm going to write it this way instead. Q over C equals IR, or I equals Q over C. Q over RC. So there's that little RC. So I equals Q over RC. Let me just clean that up so it looks a little bit nicer. Q over RC. Great. So I equals Q over RC. Well, how does that help us? Let's think about this current. Where is this current coming from? Well, that current is coming from charges leaving the capacitor. So as that current flows, and again, we're pretending that positive charges move. As that current flows, the charge on the capacitor is going to diminish and diminish and diminish and diminish. So we can actually write ourselves, there's our loop law. We can actually write ourselves this little additional thing, where instead of current, we can write that our current is given to us by negative dq dt. Why can I write that? Well, our current is already the rate of change of charge in coulombs per second, but where is this current coming from? every drop of this current is coming from charges leaving the capacitor. So you can kind of see that as the current goes, it's reducing the charge on the capacitor and reducing the charge. So what we end up with is a differential equation that looks like this, that looks like dq dt equals negative q over RC. So again, just to refresh where that came from, we arrived at this differential equation over here, which is I equals Q over RC. And then we replaced I with this negative dq dt. So this is a special kind of differential equation called a separable differential equation. So what I'm going to do is I'm going to separate. I'm going to get all my q's on one side and everything else on the other. So I'm going to bring this q over here, and I'm going to write dq over q. And that's going to equal over here negative dt over RC. All right, so now I want to do a little integral. I want to do a little integral here, and so I'm going to integrate both sides of my equation. I'm going to integrate both sides of my equation. Yes. So on my left side, right, I started out at some initial charge Q0. And again, at some time later, I want to kind of see at some time t, at time t, what's Q. So I'm going to integrate. I started off with some charge Q0. Later on, I'm going to end up with some other charge Q. And over here, I'm going to do this integral from time equals 0, when I first started, to whatever time t I have. These are both pretty good integrals. I know dq over q is ln, so I'm going to end up with ln of q from q0 to q on this side. And on the other side, I'm going to end up with, well, dt is just t. So I'll end up with negative t over RC from sometime 0 to sometime t. Okay, my ln side, I happen to know that if I do ln q minus ln of q0, you might remember that that's equal to the natural log of q over q0. And that's just going to be equal to, and I plug in my bounds here, I just get negative t over RC. And now what I can do is I can raise both sides to the e power. And so what I find is that for this discharging capacitor, after a little bit of manipulation, I get Q equals Q0 times e to the minus t over RC. And this is our first really critical equation. This is our really critical equation. So let's examine that for a moment. Usually, instead, we write it this way, where Q equals Q0 e to the negative t over tau, where tau is this time constant, is this thing called time constant. Why do we call it a time constant? Well, it's got units of ohms times farads. So let's just remember what these are. So an ohm, let's see, V equals IR. So R equals V over I. So this has units of amps. Nope. Volts over amps. And farads, I happen to know, are coulombs per volt. So my volts go away, and I end up with coulombs over amps. But amps are just coulombs per second. So my units here are in fact just seconds. So my time constant is measured in seconds. So this factor RC is what's called the time constant. And what this time constant encodes is roughly speaking, how long does this RC circuit take? How long does this capacitor take to charge or discharge. So if I have a bigger C, a bigger capacitor, it takes longer to charge. If I have a bigger resistor, the resistor slows down our current, it takes longer to charge or discharge in this case. And again, just as a reminder, this is equal to our initial charge, e to the minus t over RC still. Okay, let's look at a graph. So what happens to this thing over time? Once I start discharging my capacitor, this is an exponential decay curve. So at first, the charge on it decreases very rapidly. There's a very high current. And then it kind of slows down and smooths out. And asymptotically, approaches zero. So it does, in a theoretical sense, it never fully discharges. For all practical purposes, it eventually discharges. The remaining charge is really, really tiny. So our charge decays exponentially. It kind of goes really fast at first and then slows down. So again, we've got the charge on a capacitor here. Remember, the capacitor voltage is directly related to it by, V equals Q over C. So if we just divide away our capacitance, our voltage also exponentially decays. And then the current can be found in the circuit by just the rate of change of charge. And you do a little bit of math, and hopefully we can convince ourselves that our current also exponentially decays. So our current changes very rapidly at first, and then eventually peters out to nothing. So we get, when we discharge this capacitor, we get a sudden burst of charge, of current, of voltage, and then everything kind of slowly peters out. So the current also decays exponentially. And so you might imagine how this is used. This is used a lot in camera flashes and things like that. You connect that capacitor and you get a certain burst of current, which turns into light, and then it rapidly decays. These get used any place you really need to store electrical energy and then release it all at once. For charging, what we find is actually the situation is mostly reversed. So if we hook up a battery, and we'll do this in our lab, if we hook up a battery to our resistor and our capacitor, what happens is if the capacitor is empty at t equals 0, then what happens is that the capacitor actually kind of exponentially decays upward. It like kind of goes doo. It rapidly charges at first, and then asymptotically approaches being fully charged. It's important to note, once it's fully charged, like let's say it is fully charged, what you're going to find in your loop, let's think about what we find in our loop. If it's fully charged, you can't put any more charge on it. And so what you're going to find is that when it's fully charged, that our current is equal to 0. Our current's going to slow down and stop eventually. And if our current is equal to 0, the voltage across our resistor is also 0. And so basically, the current will stop. You'll get charges flowing and flowing and flowing and flowing until the capacitor is full, and then it will block all current. And so there's this argument that I'm going to make, and a way that I like to contextualize thinking about RC circuits is that a capacitor acts a bit like a resistor sometimes. It's not a resistor, but it kind of acts like a resistor, which has no resistance when it's empty, and infinite resistance when it's fully charged. So what do I mean by that? And again, like I said, let's kind of consider that. If my charge is increasing over time and kind of exponentially approaches my full value, what is my current? Reminding ourselves that that I is going to be the rate of change of charge. In this case, it's the positive derivative because our charge is increasing over time. So if I take that derivative, let's see, I'm going to get, well, I still get Q max out front. It's just a constant. My 1 goes away. And so I get a negative e to the t over tau times negative 1 over tau from the chain rule. So let's see, my negatives cancel out. What was tau again? Tau was RC. So this is going to be Q max over RC, e to the minus t over tau. Let's see, Q over C, I happen to know is voltage. Oh, I see. This is going to be, and voltage divided by resistance is just current. So this is actually going to be whatever my maximum current is, e to the negative t over tau. So our current, even though our charge is charging up, our current is actually going to start off at some Imax, which will just be equal to V over R, the voltage of our battery divided by R. So it kind of pretends like our capacitor is not there. Because if I walk around my circuit, right, when my capacitor is empty, if Q is 0, it's not using up any voltage. So at first, our resistor gets all the voltage, and then as our capacitor gets more and more charged, the current in the circuit drops and drops and drops and drops. But at first, I equals V over R. It looks like the capacitor is not there. So the way that I like to say this is that a capacitor acts a bit like a resistor that has an R, and I'm putting giant big air quotes around here because it doesn't really have, it's not really a resistor, but it acts a bit like a resistor that isn't there when it's empty. It acts like bare wire. And when it's fully charged, it basically blocks all current. So it acts like an infinite resistor when it's fully charged. So it offers, it doesn't stop anything when it's empty, and it stops everything when it's charged. So let's look at an example quickly of a real multiple choice question. So here we've got an RC circuit. Actually, there's a little bit of parallel stuff. And so we've got a battery of voltage V and 2 resistors and a capacitor in there. And so it asks us these two questions, and I want you to take a minute to try to answer them one at a time. So the first question is, immediately after the switch is closed, which of these expressions represents the current at the battery? So take a moment and try to do that. All right, well, let's take a look at that. Just at the moment when the switch is closed, let's look at our circuit. So the current has to run through R1, and then it gets a choice of running through either C or R2. Now remember, at first, at t equals 0, there's no charge on the capacitor. And so what's the voltage on the capacitor? Nothing. So this path, an uncharged capacitor looks like empty wire. So all the current is in fact going to choose to go through here. None of it's going to go through R2, because why would you choose a path with some resistance when you can choose a path with no resistance? So at first, it's all going to go through there, and our current is going to be V over just R1. So that's going to be B. So now try 58, remembering that after a really long time, the capacitor blocks all the current. Well, if you answered A, you are in good luck, because in this case, for this one, the way we might think of this is that when our capacitor is fully charged, it's going to block any current from going through it. And so our loop looks like that. It has to go through R1 and R2 in series, and so we get that. So remember, a capacitor that's empty lets in all the current. A capacitor that's fully charged blocks all the current. All right. So, So a lot of times these questions will ask like right after the switch is closed, which I sometimes call the transient, versus a long time after, which I sometimes call the steady state. But the idea is that you always have to, our capacitor is either always going to go from charged to discharged or from empty to fully charged. And you want to make sure that if the capacitor is fully charged, it blocks all current. If the capacitor is empty, it allows full current. So we'll do a lot more examples of that in class. What we're going to be doing, so here's a little summary and then I'll talk about tomorrow, is for our summary is we use our loop law to set up our differential equation. We solved that to find that the charge changes exponentially. This exponential decay towards the either fully charged or fully discharged, with some time constant, tau equals R times C. And that the capacitors allow full current. They don't use up any voltage when they're empty, and they block all our current when they're full. What we'll be doing tomorrow is we will be building an RC circuit. We'll be using a multimeter to track and take data on voltage versus time. And we'll be using our data to determine the capacitance of an unknown capacitor. And we're going to do that by trying to determine what is tau. We'll have a known resistor, and hopefully we can find our unknown capacitance. So your question to ponder is, if this is our voltage for a discharging capacitor, and it is, and I want to ask this in class tomorrow, and I collect voltage versus time, what should I plot? What should be my axes if I want a line? So notice that there's an E in here. What should I plot on which axis if I want a line? And spoiler, it's actually going to be a line with negative slope. All right.